Good morning to all. I'm R. Swarnalakshmi, Assistant Professor, Department of Physics, Government College of Engineering, Tanjavur. We are discussing magnetic properties of material. This is lecture 2 under magnetic properties of material. In the lecture 1, we defined various terms such as magnetization, magnetic field, magnetic induction, magnetic permeability, susceptibility, etc. And based on the value of permeability and susceptibility, materials are broadly classified into three types. The diamagnetic material with small negative values of susceptibility and relative permeability less than 1. Paramagnetic material with small positive values of susceptibility and relative permeability greater than 1. And ferromagnetic material with large positive values of susceptibility and permeability. A diamagnetic material is one in which there are no dipoles present in the absence of the external field. The magnetic moments due to the spin and orbital motion of the electrons are paired and hence there are no dipoles present. But with an applied field, a weak magnetic induction is produced in a direction opposite to the applied field. This may be due to the change in the orbital motion creating a weak magnetic induction. The dipoles are induced and aligned opposite to the applied field. It is a weak form of magnetization. It is present only when external field is present. It is a non-permanent phenomenon. Once the external field is removed, the magnetization vanishes. When placed between an electromagnet, a diamagnetic material moves to regions of weaker field. This is because the induced magnetization is opposing the applied field. As I told earlier, due to changes in orbital motion, a weak induction is present in the direction opposing the applied field. Some of the examples of diamagnetic material are gold, germanium and silicon. Since it is very weak, diamagnetism is observed only when all other forms of magnetism are absent in a material. Hence, it is of no practical importance. Paramagnetic material. As you can see, unlike diamagnetic material, there are dipoles present in a paramagnetic material, but in the absence of external field, the net magnetization is 0 because the dipoles are oriented in random direction. With an applied field, they tend to get oriented along the field direction, producing a net magnetization. But once the external field is removed, they revert back to the situation of random orientation. Hence, this is also a non-permanent form of magnetization. Due to the incomplete cancellation of electron spin and orbital moments, there is a dipole moment associated with each atom, but they are randomly oriented. Some of the examples of paramagnetic material are air, aluminium, magnesium, platinum and Fe2O3. Ferromagnetic material. They are permanent magnetic material with very large positive values of susceptibility and relative permeability. Examples are iron, nickel, cobalt and gadolinium. The large permanent magnetization can be explained using the domain theory. Domains are regions over which adjacent dipoles are oriented along the same direction. In the absence of external field, the magnetization is still zero. But the uncancelled spin magnetic moment, in addition to a small contribution from orbital magnetic moment, undergo coupling interaction and cause alignment of adjacent dipoles in the same direction. This mutual spin alignment exists over large volumes of the material, and these large volumes over which all the dipoles are aligned in the same direction are called domains. Domains have adjacent dipoles aligned in the same direction. Direction of alignment and hence the magnetization vary from one domain to another. The net magnetization is the weighted fraction over the volume. Consider this example. You have three domains 1, 2, 3 in this material. Let V1 be the volume of domain 1, V2 the volume of domain 2, V3 the volume of domain 3. Then the net magnetization M is given by 1 by V times V1 M1 plus V2 M2 plus V3 M3. Note that this is a vector addition because the direction of magnetizations are different. So this is called weighted volume fraction. Further on with domains, the domain wall is a region which is of the order of few microns, which means there are tens of thousands of atoms in this region. And you can see in one domain the dipoles are oriented upward, whereas the adjacent domain the dipoles are oriented downward. But there is not an abrupt change across the domain wall. Instead, there is a very gradual change in the orientation as seen here. This is one of the characteristics of the domain. There is a gradual change in the magnetic dipole orientation across a domain wall. When an external field is applied, we will consider a specimen like this now. You have 4 domains and I am just showing the net magnetization alone, which is the vector sum of all the dipoles present in that region. So you have 4 domains that are randomly oriented and hence the magnetization initially is 0. At H equal to 0, the magnetization is also 0. As the external field increases, you can see that the domains that are favorably oriented, the field direction is given by this direction. The favorably oriented domains grow at the expense of the unfavorably oriented domains. This continues till the entire specimen becomes a single domain. And this happens by movement and rearrangement of the domain walls. After becoming a single domain, all the dipoles get oriented along the external field direction. This corresponds to saturation magnetization given by MS. Domains change shape and size by movement of domain boundary. As the strength of the H field increases, that is the external field increases, domains that are oriented in the direction favorable to the applied field grow at the expense of unfavorably oriented domains. This process continues till the specimen becomes a single domain. Saturation magnetization MS is attained when all dipoles are mutually aligned with the external field. One of the characteristics of saturation magnetization is that it decreases with increase in temperature. This is because as temperature increases, the atomic vibration increases, and this leads to destruction of the spin coupling interaction. This happens at a temperature called Curie temperature Tc. The relation between susceptibility, recall that susceptibility is m by h. The relation between susceptibility and absolute temperature is given by C by T minus Tc, where C is a constant, T is the absolute temperature, Tc is the Curie temperature. Here I have listed out the Curie temperature of few elements. For iron, it is 768 degrees centigrade. For cobalt, it is 1120 degrees centigrade. For nickel, it is 335 degrees centigrade. And for Fe2O3, it is 585 degrees centigrade. Representing this relation graphically, we have a graph of this form for a ferromagnetic material. 1 by chi versus T curve will be a straight line with an x-intercept at Tc. Above the Curie temperature, the ferromagnetic materials will behave like paramagnetic. This law is known as Curie-Weis's law. Proceeding further with the domains. Domains are formed such that the net energy of the system is minimum. Some of the energies associated in the formation and movement of the domains are exchange energy. It is the energy that arises due to the mutual alignment of adjacent magnetic moments. And this alignment is such that it does not violate the Pauli exclusion principle. More the alignment, less is the exchange energy. Magnetostatic energy. Magnetostatic energy is the energy that increases with the increase in the alignment of the dipoles, and it is high at the surfaces. Anisotropy energy. This arises because the field required to magnetize the material along different direction is different. For example, in case of BCC iron, 100 plane is easily magnetized for the same field compared to 111 plane. Whereas in case of nickel, 111 plane is easily magnetized compared to 100 plane. The excess energy required to magnetize a specimen along a particular direction is known as anisotropy energy. Domain walls, we have seen that there is a gradual change in the orientation of the dipoles across the domain walls. The domain wall thickness is decided based upon an optimal value of exchange energy and anisotropy energy. The exchange energy is minimum if the change is very slow across the domain wall and the domain walls are thick. Whereas anisotropy energy is minimum if there is an abrupt change, that is the domain walls are thin. The size of the domain walls are such that an optimal value of exchange energy and anisotropy energy is achieved. And also another factor in the formation of domains is that the net energy is kept low. Magnetostrictive energy. This is expansion or shrinking of the specimen due to magnetization. It is also known as magnetoelastic behavior. The magnetostrictive energy causes change in dimension of the specimen when taken through a cycle of magnetization. So with this, we wind up the discussion on domain theory of ferromagnetism. In today's lecture, we have discussed about the characteristics of diamagnetic material and paramagnetic material. We have discussed elaborately the domain theory of ferromagnetism and the temperature dependence of saturation magnetization. We will continue with the hysteresis curve and classification of hard and soft magnetic material in lecture 3 on magnetic properties of materials. All the best.